Hello, thank you so much for tuning into my YouTube channel. Today's video is going to be a tutorial on hyperspectral image classification using CNN in PyTorch. Let's get started. As I said in today's video, I'm going to talk about hyperspectral image classification using a deep CNN in PyTorch. Before we start, you should know that this video is an extension to a former video that I already made. So I'm not going to go in depth for so many of the concepts. And if you need more explanation, just go to this video that is already on my channel. In this video, I'm going to do what I did in that video, but in PyTorch. In my former video, I coded a deep CNN in TensorFlow, but here I'm going to do it in PyTorch. So it's going to be a same network, but in PyTorch. Hyperspectral imaging is an advanced technique that captures images across a wide spectrum of wavelengths extending beyond the visible range into the infrared and ultraviolet. This results in a detailed spectral signature for each pixel, allowing for precise identification and analysis of materials and objects based on their unique spectral properties. The integration of artificial intelligence, particularly machine learning and deep learning algorithms, has significantly enhanced the analysis and interpretation of hyperspectral data. The synergy between HSI and AI has led to advancement in various fields including agriculture, environmental monitoring, medical diagnosis, and food quality control. The architecture of a typical deep 2D CNN for hyperspectral image classification includes multiple layers designed to extract and learn features from the input data. The layers include input layer, convolutional layers, activation functions, pooling layers, dropout layers, fully connected layers, and output layer. This architecture enables the model to learn both spectral and spatial features from hyperspectral data, leading to accurate classification and analysis. The data that we're going to use is Indian Pines dataset. Let's go to Python and show you the code. As you can see, I have coded this problem in Google Colab. First, we're going to be installing the necessary libraries. Especially I know that Google Colab doesn't have spectral library. And then we're going to be importing the necessary libraries, as you can see here. Then here we're going to be importing PCA to reduce the dimensionality of the data, and then other libraries that we need, including PyTorch. And then here we're going to be mounting Google Drive, and here is the path to my data, and here is where we're going to do some reproducibility, meaning this is about making runs repeatable, so we can get the same splits, same initial weights, and same dropout masks, and therefore the same results each time when we rerun, right here. And then here we're going to be choosing GPU if present. If not, we just want to go with CPU. And then here is where we're going to be loading the data. And then here is where we're going to be applying PCA for dimensionality reduction. And then here we're going to be reducing the bands to 30 principal components. And here is where we're going to be creating patches for training. So the patches are windows of size 15 by 15. And then here is where we're going to be building the training samples and their labels. And here is where we're going to be also removing the unlabeled samples, label 0. And here is where we're going to be converting the data into PyTorch tensors. So the feature tensors are float 32 and labels are integer. And here is where we're going to be wrapping arrays as PyTorch dataset. And here is where we're going to be iterating batches during training and evaluation. And here is where we're going to be counting distinct labels after filtering. So this is where we're going to be declaring a standard NN model, neural network. As you can see, this is the first block, second block, third, fourth, and then the dance layer. Of course, before that there's a global average pooling, and this is where they're assembled together. So the first block has a 2D convolutional followed by ReLU, another 2D convolutional, another ReLU, and then max pooling, and then the dropout rate is 0.3. The dropout here helps prevent from overfitting. And then the second block, and then the third block, fourth block, and then after the fourth block there's a global average pooling, and then right after that there's a dance layer. Here is actually where the classification is going to be done. So the head flattens to 512 and it applies a 512 to 512 with ReLU activation function. It has a dropout of 0.5 as well. And then at the end there's a final linear to class logits. So we haven't used softmax for it. Here's where the network is assembled together, and this part of the code creates a network with 30 inputs channel, which is from PCA bands, and then moves it to either CPU or GPU. And here is where we're going to be assembling the loss and optimizer. The optimizer is going to be added with a specific learning rate, and as I said, we're not going to be using any softmax. And here is where we're going to be computing the average loss and accuracy across the given loader. And here is where we're going to be keeping tiny log of metrics per epoch. And here is where the whole training is going to be done. And we're going to be also printing the progress. And here is where the whole visualization is going to be done. This part of the code is going to pad the image so we can extract a centered 15 by 15 patch at every pixel. And this part of the code is going to be sliding across the whole image, and then it's going to collect every pixel centered patch. And then this part of the code is going to convert to channel first tensor and then does batched inference without gradients. And then this part of the code is going to be reshaping the flat predictions back to an image. And then here the unlabeled pixels are going to appear at 0 in the masked plot. And this part of the code is going to produce 3 figures: the ground truth, full prediction, and masked prediction. And this is where the visualization is going to be run. I already ran this for 20 epochs. As you can see, this is the predicted, this is the original, this is the ground truth, and this is the predicted. This is the masked predicted. As you can see, the result hasn't been that bad. You could have access to this code using the link in the description section of this video. And as I said, this is just an extension to the video I did before. In that video I used TensorFlow, but here I'm using PyTorch. In the next video, as you can see here, I'm going to show you an enhanced version of this network here. But for now, that's about it. Thank you so much for watching this video. I hope you liked it and also found it helpful. If you liked it, I would appreciate it if you could subscribe to my channel and also share the video with your friends. Thank you so much and have a nice day.